We've already gone through the evidence that the cortex and the hippocampus correspond respectively with the modular hierarchy of condition definition and the condition change manager. So we're next going to look at some subcortical structures and compare the predictions about the properties of the behavior selection subsystem with the observed properties of the basal ganglia, the thalamus, and the basal forebrain. This is the list of detailed expected characteristics, and we'll now go through each of the predictions about the component hierarchy of behavior selection. As discussed earlier, many of the predictions derive from the use of consequence or reward feedback to guide future behavior. It's a major source of information for learning, but has the limitation that it's always specific only to the recent behaviors. A major prediction is that there must be a separation between the modular hierarchy we've already discussed and a subsystem that interprets condition detections as behavior recommendations, selects and implements the most strongly recommended behavior, and following the behavior uses consequence feedback or rewards to modify the recommendation weights that led to the behavior. There's a clear contrast in the brain between the cortex, with its multi-directional internal connectivity corresponding with the information exchanges expected in the modular hierarchy, and the subcortical structures with their much more structured connectivity patterns. The simpler pattern of connectivity can be seen, for example, in the thalamus, where each thalamic nucleus communicates with a different cortical area via its own region of the TRN, and the very specific paths between cortex layers and thalamic nuclei, plus the precisely targeted connectivity between the various subcortical structures, and on an even more detailed level, the striking pattern of connectivity between the nuclei of the basal ganglia. All this is in contrast with the much less structured pattern of connectivity within the cortex. In addition, the expected information processing sequence would be that first, conditions are detected that recommend behaviors, and second, the behaviors selected and implemented. So it's significant that if you observe the neural activity related to changes in, for example, the position of a limb of the body, activity occurs in the cortex somewhat earlier than in the subcortical structures. The theoretical considerations also predict that modules in the cortex are behaviorally ambiguous, but different components in the behavior selection subsystem will correspond with different specific behaviors. In this picture of the rat brain, this is the striatum of the basal ganglia in one hemisphere, where it's observed that individual neurons, or small groups of neurons, correspond with very specific behaviors, such as moving a limb in a specific direction or using specific muscles. And as a rat performs a sequence of movements, there'll be activity in a sequence of different regions of the striatum corresponding with each movement. And this correspondence between neurons and behaviors is also observed in the GPI-SNR. Another prediction is that any behavior must be recommended by a large number of different receptive field detections, and one receptive field detection must recommend a wide range of different behaviors. And this is a typical neuron in the striatum, corresponding with one behavior. And as predicted, one cortical neuron targets lots of different striatal neurons, recommending all the corresponding behaviors. And one striatal neuron like this gets perhaps just one input from a very large number of different cortical neurons, and needs a large group of active inputs to fire, although many different combinations of its cortical inputs could make up such a group. In other words, you need lots of cortical recommendations to get a behavior. Another prediction is that each recommendation must have an individual weight that can be independently adjusted. And as expected, a cortical synapse onto a striatal neuron is located on a spine, partially isolating it from the other synapses so that the weight of any one synapse can be changed independently. And synaptic weights can either decrease or increase, with decreases in synaptic weights being somewhat more prominent in the striatum than in the cortex, as you'd expect, because recommendation weights need to be adjusted both up and down, depending on whether the consequence feedback is positive or negative. Another prediction relates to the resource costs of information flow. Conditions must be detected at many different levels of complexity to be able to recommend behaviors in response to individual features or individual objects or different groups of objects, and even more complex circumstances like groups of groups and so on. It'll be too costly in resource terms to simultaneously process all the available sensory information to detect conditions within all the different objects, all the different possible groups of objects, and all the possible more complex circumstances all at the same time. So the releases of information from an area detecting conditions on one level of complexity to an area detecting more complex conditions must be limited. And such releases are themselves critical behaviors which must be recommended and selected. And within the subcortical structures, there's the thalamus, which has substantial interconnectivity with the cortex, but doesn't appear to modify cortical information. And the reason we believe that is that because damage to the thalamus results in exactly the same deficits as those resulting from damage to the corresponding cortex. And recall that subjects with brain damage to either the right hemisphere cortical visual association areas or to the right pulvinar thalamic nucleus show the same neglect syndromes. They don't process sensory information coming from the left visual field. So if the patient was asked to search for letter T's among the L's in the visual field that's illustrated, eye movements of such a person are limited to the right visual field, and that limitation occurs either with cortical damage or with thalamic damage. However, the thalamus does appear to play a role in releases of information, for example its role in attention or implementing selections of the objects to be processed further by the cortex. Another prediction is that there'll be different components in the behavior selection subsystem that correspond with different types of behavior. And it's indeed observed that there are parallel paths through the basal ganglia and thalamus that support motor, eye movement, and some different types of cognitive behaviors. There's a predicted need for a separation between selection of strategic and more tactical and more detailed behaviors. And it's observed that the more dorsal parts of the striatum are concerned with motor movements, while the ventral parts are concerned with complex decision making. Then there's a series of predictions that mechanisms will be needed to address a range of constraints on behavior selection. And to see how the subcortical structures confirm these predictions, we need to look at the connectivity in a bit more detail. I'll quickly run through the evidence, and a little later on I'll discuss it in more detail as part of considering the information models for the basal ganglia and thalamus. The striatum is getting lots of inputs from the cortex that it interprets as recommendations. To make sure the behavior with the strongest recommendation strength is selected, there are two parallel paths. A neuron signal in the direct path can be understood as carrying a recommendation in favor of its corresponding behavior, and on the indirect path, a recommendation against any behavior except that one. The most appropriate behavior is then selected in the GPI-SNR. But if it looks as if no behavior or more than one behavior is about to be selected, the feedback loop through the SNC back to the striatum shifts the ratio of activity between the direct and the indirect paths to correct the situation. And this feedback loop adjusts the number of neurons firing in the tonic mode. So it shifts the level of background dopamine in the striatum, adjusting the relative activity of the D1 and D2 neuron populations. Changes in recommendation weights are critical behaviors. They have very strong effects on future system performance. So weight change behaviors or reward behaviors must be recommended by cortical receptive field detections and selected in the basal ganglia. In this case, the behaviors don't release cortical information, but act back into the striatum to change weights. Burst firing of dopamine neurons in the SNC is triggered by certain receptive field detection via the striatum and results in synaptic weight changes in the striatum. There's also mechanisms that prevent weight changes if the behavior has often been rewarded in the past, but I'll discuss these a bit more later. One of the problems a learning system faces is that sometimes reward feedback can be just strategic, and the example I discussed earlier was a musician being applauded at the end of a concert, and that's good for rewarding decisions to give the concert and perhaps the choices of music, but it isn't sufficiently discriminating to change the recommendation weights in favor of every detailed muscle movement while playing, say his violin. But as we discussed, a strategic reward signal is appropriate to reward the decisions that selected the strategic behavior, but it could also reward the reward behaviors that reward the more detailed muscle movements. In other words, the applause indicates that the way the musician's been practicing is good. As we'll describe later in more detail, the midbrain dopamine neurons implement reward behaviors back into the striatum, and there's a spiral of connectivity between these structures in which strategic rewards reward strategic behaviors and somewhat more tactical reward behaviors. More tactical rewards reward tactical behaviors, and also more detailed reward behaviors, and so on. There's a bit more that needs to be said about information releases. A detailed mechanism to release cortical receptive field detections is needed. And as we discussed, a possible mechanism is to place a frequency modulation on the neuron outputs so that the action potential spikes are bunched together. Because the effect of one spike decays within 8 milliseconds, spikes bunched together within that length of time will have a much stronger effect on their targets. If the thresholds of the target neurons are set so that unbunched spikes produce no firing, then the bunching is effectively a release of information. The TRN in the thalamus is located on the path between the thalamus and the cortex, and it can place a gamma band modulation on selected cortical areas, which therefore implements the required information releases. And a final point about the behavior selection subsystem. Sometimes the exact timing of an information release may be critical. To give an example, think about the process for selecting the appropriate columns for receptive field expansion. Identifying the appropriate columns requires a competition process in the dentate gyrus and CA3. And once that process is complete, CA1 uses the results of the process to send signals to drive the appropriate expansions in the cortex. But there's massive activity in CA3 and the dentate gyrus during the selection process, and the connectivity between CA3 and CA1 is always in place. So the problem is that action potential spikes could pass along that connectivity while the competition is still underway, resulting in signals driving receptive field expansions derived from the middle of the competition process, and those signals won't correspond with the correct final selections. So the system has to ensure that outputs to CA1 and beyond aren't effective until the selections are complete. The basal forebrain addresses this issue, and in the case of the hippocampus, it's the septal nuclei in the basal forebrain. The basal forebrain gets inputs over the fornix that indicate the state of the competition, and once it's complete, the septal nuclei impose a theta band modulation on top of any existing gamma band. The spikes are even more bunched together, reaching the level where receptive field expansions occur. And as expected from this model, damage to the septal nuclei removes the ability to create new decorative memories. So that concludes our overview of the evidence that the thalamus, the basal ganglia, and the basal forebrain correspond with the predicted component hierarchy. And in the next section, I'll go on to the information processes performed by the individual structures in more detail.